కామర్స్ 2వ సంవత్సరం విద్యార్థుల కోసం బిజినెస్ స్టాటిస్టిక్స్ నుండి యావరేజెస్ అనే పాఠం ప్రసారమవుతుంది.
Dear students, you are welcome to a lesson in business statistics on a topic averages drawn from block 2 of business statistics course. Today's lesson is on averages, and one of the important objectives of statistical analysis is to get one single value that describes the characteristic of the entire mass of unwieldy data. Such value is called a central value or an average. The word average is very commonly used in day-to-day conversation. Hardly a day goes by that we do not make a reference to the word average. We often hear people making certain statements making use of the term averages, such as average marks, average students, average height, average weight, average speed, average mileage, and so on. Now, all these things are used only to best describe the characteristic of a mass of data, just to get an idea as to what it is about. For example, when you insist that you are an average student, it means that you are neither very good nor very bad. It only means that you are a mediocre student. However, in statistics, the term average has been used and defined differently by different statisticians. We will take a look at the popular definitions. For example, Clark has defined average as an attempt to find one single figure to describe the whole of the figures. In the same way, Lebo has also attempted to define the term average as a number which is typical of the whole group. Further, Croxton and Cowden also have attempted a definition of the term average as a single value within the range of the data that is used to represent all of the values in the series. Since an average is somewhere within the range of the data, it is also called a measure of central value. A close look at the definitions gives us a clear idea that an average is a single value that represents the whole group of data. Since an average represents the entire data, its value lies somewhere in between the two extremes, that is, the largest value and the smallest value. For this reason, an average is frequently referred to as a measure of central tendency. Now, we try to understand the objectives or why we should study averages at all. An average, as mentioned earlier, gives us a bird's eye view of the huge mass of data, which is not easily understood. In fact, the human mind is incapable of grasping all the mass of data and the details of large numbers and their interrelationships. Hence, we study the averages. The objectives of averages are to arrive at a single value. For example, we talk in terms of per capita income of citizens or people of a particular country. To facilitate comparison, for example, within one particular time period between two or more variables, or over a period of time within the same class of variables. For example, when we take the average marks scored by a student in the first year and the second year, this is actually an inter-time comparison. The second class of comparison could be students scoring different sets of marks, and when their performance is compared in terms of one against the other, we can always say who is a better student when compared to the others. 3. To facilitate statistical inference based on the analysis of the data which was collected, tabulated, classified, codified, and put to some kind of a statistical treatment, we can always say that we can draw some statistically valid inferences based on certain computations and calculations. 4. It definitely aids in decision making. For example, knowing about normal the output and comparing it with the actual output, we can always say whether a particular company is lagging behind in terms of achieving its slated goals. Let's now try to understand or know the qualities or the requisites of a good, which is an ideal average. Basic question is, do we have anything like conditions to be fulfilled by an average to be accepted as a representative of the whole group of data from which it is actually drawn? Since average is a single value, as mentioned earlier, representing a group of values, it is desirable that such a value possesses or satisfies the following conditions, which are called the requisites of a good or ideal average. Number 1, an average to be ideal should be easy to understand. 2, simple to compute so that it can be widely used. 3, it should be based on all items. For example, when you have observations whose values are 10, 20, 30, 40 and 50, the total of the observation comes to 150 and the number of observations is 5. So, we get an average 30. Now, if it is not based on all these items right from the first one till the last one, it is quite possible that the average is distorted and definitely it reduces the usefulness of the average calculated. And the average to be an ideal one should also be rigidly defined. It only means that the average should not depend or should not be affected by the bias or the prejudice of the investigator, so that it really doesn't lose its statistical usefulness in a limited sense. And finally, an ideal average should also lend itself to an algebraic treatment, that is further statistical treatment. For example, with the help of the arithmetic mean or any of the averages, you can still have lot of scope for moving on to calculating the different other averages or statistical measures. For example, with the help of arithmetic mean of series 1 and series 2, you can always find out the combined average for both these series. Now, we try to understand different measures of central tendency. We take a look at this chart. There are different measures of central tendency. They can be classified into 3 groups. 1, the mathematical averages, the positional averages and the special averages. Under the mathematical averages, you find arithmetic mean, geometric mean and harmonic mean. Positional averages, you have median, mode, and a special averages category, moving averages and progressive averages find a definite place. Now, today's discussion is limited only to the first one under the first category, that is the mathematical averages. We will be discussing only about arithmetic mean and its calculation by making use of the data given under the individual observations, then discrete series and the continuous series. We will take up the calculation part. We will try to understand the computation of arithmetic mean for individual series by using the direct method first. The computation of arithmetic mean for individual series can be done either by using a direct method or a shortcut method. We will try to understand the computation of arithmetic mean for an individual series by using direct method. We take a look at the example. Assume that the values of a variable x are 3, 4, 5, 6 and 7. The steps involved in computation of arithmetic mean for an individual series by using a direct method are very simple in nature. There are 2 steps in number. Number 1 is to arrive at the total of the values of variable x by adding up all these figures, and in this example, when you add up all these figures, you get 25. Let that figure 25 be denoted by sigma x, which is the total of the values of the variables. And the second step is to arrive at the number of observations, and that be denoted by letter n, which represents the number of observations. The formula used for computation of arithmetic mean for individual series by direct method is x bar, which is the arithmetic mean, is equal to sigma x by n, and we have already arrived at these figures. That is, sigma x is 25 here, and n, which is the total number of observations, 1, 2, 3, 4 and 5, be n here, that is 25 divided by 5 will give you arithmetic mean 5. Now this value, which is the arithmetic value, which is otherwise known as a measure of central value, lies somewhere between the largest and the smallest values. Thus the name arithmetic mean here, or otherwise called central value. Now we try to understand the computation of arithmetic mean by using shortcut method, of course using the same data or same values here. Now the steps involved here are 4 in number, to be very precise. 1, take an assumed mean and denote it by letter A, which stands for the assumed mean. 2, take the deviations of the items from the assumed mean and denote these deviations by the letter D. 3, obtain the sum of these deviations, that is, add up all these deviations and let them be denoted by the sigma D sign. And finally the fourth figure is apply the formula, which is x bar is equal to assumed mean plus the total of the deviations taken from an assumed mean divided by n. Let's take a look at this example, which involves a lot of calculations. The values of variable x, we just for simplicity's sake, we take the same data to repeat 3, 4, 5, 6 and 7, where n is the same as we have seen earlier, that is 5. Then first step, as we have discussed here, take the assumed mean. It's not necessary that we should take any one of the values of the variable given as an assumed mean. You can take any value, but for a simpler understanding of the whole process, we take one of these values. In this example, it's 5, which is taken as an assumed mean here. Then for obtaining the deviations, what we have to simply do is deduct the assumed mean from the values given here. For example, the first one, it is x, which is the value of the variable, minus assumed mean, which is 5 here. 3 minus 5 will give you minus 2, which is denoted as D here, and then 4 minus 5 is minus 1, 5 minus 5 will give you 0, 6 minus 5 will give you plus 1, and 7 minus 5 will give you plus 2. The third step, which says obtain the sum of these deviations, that is, add them up to get the total of the deviations taken by the variable from an assumed mean, which is denoted here in this case as sigma D, which is equal to 0 here, as we have minus 2 minus 1, which is 3 here, plus 1 plus 2, which is again 3. We obtain the sum of these deviations by taking into account the signs. Then apply the formula as was given at step number 4, that is, x bar is equal to assumed mean plus the total of the deviations taken by the variables from an assumed mean divided by n, which is the total number of observations here, since it is individual observation series. X bar is equal to 5, which is the assumed mean as was made clear earlier, plus the sum of the deviations taken, which is equal to 0, and that should be divided by 5. That gives you a precise figure which can be called the arithmetic mean for an individual series for a data like this, which is 5 here. The steps involved in the computation of arithmetic mean for a discrete series using direct method are 3 in number. The first step is to multiply the frequency of each row with the variable and obtaining the total, and after obtaining the total, we denote it by the expression sigma fx. The second step is to divide the total obtained by the number of observations, that is n. The third step is to apply the formula, which is x bar is equal to sigma fx by n. We will try to understand the steps here. The first step, which is finding out the total of the variables by multiplying the frequency of each row with the variable, is you have to multiply the values of the variable given 3, 4, 5, 6, 7 by the frequency given, which in this case is 1, 2, 3, 4 and 5. Then after multiplying f by x, we get fx, and when you add them up you get 85 for this particular case, and then you simply apply the formula, which is x bar is equal to sigma fx by n. Then sigma fx here is, which is the total of the frequencies after multiplying it by the values of x, is 85, and divided by the total of the frequency here, which is n, that is 15 in this case. 85 by 15 will give you a value of 5.667. Now, similar to the earlier example, which was for an individual series, we do have a shortcut method for computing the arithmetic mean for a discrete series, where the steps involved are little greater in terms of number. It has 4 steps to be followed when you calculate the arithmetic mean for a discrete series by using shortcut method. Step number 1 is take an assumed mean. As we have seen earlier, you can take any number as an assumed mean for arriving at the deviations. 2, the second step is to take deviations of the variable from the assumed mean and denote it by d here. And third step is to multiply these deviations with the respective frequencies, which are denoted by f here, and take the total and denote it by sigma fd here. Divide the total obtained in such a fashion by the total of the frequency, which is n here, by applying the formula, which goes x bar is equal to assumed mean plus sigma fd by n. Assumed mean here in this case is 5, sigma fd as we can see here is 10, and n as we can see from this particular table is 15. That is, x bar is equal to 5 plus 10 divided by 15, which gives you a value of 5.667. Kindly note that whether we use a shortcut method or a direct method, the answer remains the same, which is 5.667, as was observed in the earlier example. Now, having done the computation of arithmetic mean for the individual observations and the discrete series by using direct and shortcut method, we try to learn something about the computation of arithmetic mean for a continuous series, where we don't find anything like single values, but the values of the variable appear in terms of a range, say for example 0 to 10 or 0 to 100, 100 to 200 and so on. Now, the direct method makes use of 3 steps here. That is, the first step is to obtain the midpoint of each class and kindly denote it by letter m as is shown here. The midpoint here is the average value which we arrive at by dividing the lower limit, in this case which is 0, and the upper limit by 2. That is, 0 plus 10 by 2 will give you 5, which is the midpoint here, which is denoted by the letter m. Now, the second step is to multiply these midpoints, which we have arrived at by dividing the lower and the upper limit by 2, by the respective frequencies which are given along with the values of the variables which appear in a range of the respective frequencies of each class must be multiplied by these midpoints, and we arrive at, or we obtain, the total, that is sigma fm. The third step is to divide the total obtained in step number 2, which is the sigma fm values here, by the sum of the frequencies, which is nothing but n, that is the total of the frequencies, which is 15 here again. Then the formula goes x bar is equal to sigma fm divided by n, and the midpoints after having been multiplied by the respective frequencies as appear here is 475 divided by n, which is the total of the frequencies is 15, you get 31.667, which is the arithmetic mean of a continuous series of data which is given here. Then computation of arithmetic mean for a continuous series can also be done by using a shortcut method wherever the values are greater in number or greater in terms of complexity. Maybe they involve a lot of calculations. Then by using a shortcut method, we have to make use of 3 or 4 steps here. The first step is taking an assumed mean and denoting it by A, which stands for assumed mean here. And the step number 2 is from the midpoints, as we have seen earlier, of each class, take out the assumed mean, we get some values here, and this is the values here, and then multiply the respective frequencies which are given in the problem itself of each class by these deviations which you have taken, and obtain the total of these deviations after having multiplied them by their respective frequencies of each one of the classes, and denote them by sigma fd. And the final step goes, this is applying the formula which is x bar is equal to assumed mean plus sigma fd by n, and assumed mean here in this case is 25, and then sigma fd values are given as 100 as we have arrived at after having carried out the calculations, and divided by the total of frequencies which is n here, which is precisely 15 as is seen from here, and then 25 plus 100 divided by 15 will give you the same value as we have seen just now in the earlier example where we made use of the direct method. It is 31.667 again. We can also make use of a step deviation method where the values involved are greater again, but the calculations become too very cumbersome in the light of the numbers being large in terms of quantity, and the calculation become really difficult. Just to make the calculations part simpler, we make use of step deviation method, and the steps involved are slightly more in terms of number again, as against 4 steps we have seen in the case of shortcut method for a continuous series. As far as calculation of computation of arithmetic mean is concerned, we have 6 steps here. The first step is, as usual, we take an assumed mean, assume any figure to be your mean from which you have to take deviations, and then take deviations from the midpoints. We know what midpoints are here, they are the same old ones, as we are using the same old example of 0 to 10, 10 to 20 and so on through 40 to 50. And then in order to simplify the calculations, divide the deviations by the class interval and denote them by a letter d dash as against d. In order to simplify the calculations, divide the deviations by the class intervals and denote them by d dash. Now the next step is to multiply the values arrived in step number 3 by the respective frequencies and denoting them by f d dash. And the fifth step is to add all the values arrived at in step number 4, that is the sigma f d dash items here. Add all the values arrived in step number 4 and denote them by sigma f d dash, and finally you apply the formula which is x bar is equal to assumed mean or A plus sigma f d dash by n into I, which is nothing but class interval. In this case the class interval is 10. Then x bar, when we substitute the values, will be equal to 25 plus 10 by 15 into 10, which is the class interval here as was mentioned earlier, which gives you the same value as we have observed earlier, which is precisely 31.667. It only means whether we make use of the direct method or the shortcut method or the step deviation methods, answers or the arithmetic mean value which you arrive at after carrying out the calculations will remain the same. Having learnt the computation of arithmetic mean, which is the most important average for individual observations, discrete series and the continuous series, by using different methods, direct, shortcut and step deviation methods, I am sure we are in a better position to understand the mathematical properties of arithmetic mean. The first one, which is a very important one, is the sum of the deviations taken from the actual mean always tend to be 0. They are in fact 0. 2, the sum of the squared deviations of the items from arithmetic mean is always the least or the minimum. The third one, as one can observe from the calculations which we have already done, is the further algebraic treatment is always possible, and the arithmetic mean has got its own merit. Number one is it's the most widely used average, as it is very easy to understand and calculate, thus it tends to be an ideal average. Two, it is based on all items, even including the extreme items too. Three, it balances the values on either side of it, because it's always centers around something like a cluster of values here. And finally, it is calculated mathematical value and not a positional average like the other one, to be very specific like median or mode. Then one may tend to come to the conclusion that everything is good or positive about arithmetic mean, but unfortunately it has got a negative side too, that is, it has got its own limitations. To mention a few of them, particularly the most important ones or the chief ones, the first one is extreme items unduly always affect the value of the average. For example, you have 10, 20, 30, 40, 50 as the values of a given variable, which add up to 150, and the total number of observations is 5 here. When you divide 150, which is sigma x by n, which is 5 here, you get 30, but once you remove the extreme value like the 50 here, you get only 25 to be the average, which is slightly misleading here. 2, the average of a given distribution may give a value which is not exactly found in any distribution. For example, as we have seen in the earlier case, it could be 5 or 5.667 or 31.667, when you can really take a close look at the table and the calculations and the computed value, you don't find anything like 31.667 or 5. Maybe just by accident it is found there, but 5.667 is not finding a place anywhere in the distribution of the values of a given variable. Finally, the measure of central tendency fails to give an idea about the formation of the series itself, which is a chief limitation and which can definitely reduce its effectiveness as an ideal average.